So does everybody know where the smart class is? Okay. Now, we have okay, the midterm will be on Friday. I was planning to make a lecture on Wednesday, tomorrow, in the recitation hour, but probably it will not make any sense. You won't be interested in having any new material covered tomorrow if you show up. Well, so there won't be any lecture tomorrow, Wednesday, but there will be a lecture next week. So next week we will have 3 lectures after the midterm. So at least midterm will be over, so you will be worrying about the finals. But nevertheless, that is our last week. So we will do 6 hours next week. Now, any questions before we start? Any questions about anything that we had covered in the class? Anything you want repeated? Any particular example that you would like solved before the midterm? Now we will be continuing with magnetization today. So we will do some examples. Now the last thing we were doing last week on Friday was we were looking at the magnetic fields in material. And before that we had discussed how the dipoles, how the dipoles are influenced by an external magnetic field. We had seen that they are if there is a magnetic dipole, then it will try to align with the magnetic field. And furthermore, we had looked at an electron in circular orbit, assuming that its radius didn't change. We had seen that its magnetic dipole increases in the opposite direction to the magnetic field. So we have these 2 effects. One effect in which the component of the magnetic dipole in the direction of the magnetic field is positive, and the other effect in which the component of the magnetic dipole moment in the direction of the magnetic field will be negative. And through these 2 mechanisms, an applied magnetic field will influence a material, creating additional dipoles or aligning the dipoles, so the material will have a net dipole moment. And we define the magnetization. This is what we call magnetization. And it is the dipole moment. It's basically the dipole moment density, magnetic dipole moment density. So basically, if you have your material, you create some magnetic field in this material. Either you just exert some, apply an external magnetic field due to currents outside your system, or you send some current through the material. And so this current will create a magnetic field which will align the dipole, which will induce additional magnetic dipole moments in the system. And if you imagine a very small volume over here, delta V, it will have some magnetic dipole moment delta M, and magnetization is defined as delta M over delta V. So this is how we define the magnetization. And we already know what is the vector potential corresponding to a single magnetic dipole. This was equal to, if we have just a single dipole at the point R, this is M cross R divided by R cubed with mu0 over 4 pi. This is the vector potential corresponding to a single dipole, single point-like magnetic dipole. We can just divide our material into very small bits, each having volume dV, and then each one will contribute such a by this much to the total vector potential. So if you would just sum them up, the total vector potential at a given point R would be mu0 over 4 pi m r prime cross r minus r prime divided by r minus r prime cube dv prime. And if there is an additional current running in the system that we just send the current through the system, that will also contribute to the vector potential. So this will be the total vector potential of my system, which is magnetized. Now just keep in mind, now when we are talking about a single dipole, we use this notation R, but keep in mind that this R is not the position vector of my point to an arbitrary origin. This R is the position vector at which the position vector relative to the dipole of the point at which I'm evaluating the vector potential. So that is why here my dipole is at the point R prime. So if R is the point at which I'm evaluating this vector potential, then the relative position of that point R relative to my dipole is just R minus R prime. So this is why here it appears the R minus R prime and not R. And now we had seen that we can rewrite this term in the form mu0 over 4 pi jr prime plus jb plus mu0 over 4 pi kb at r prime ds over r minus r prime, where this jb is nothing but the curl of our magnetization, and kb is our magnetization cross the normal to my surface. I think this is where we had left on Friday. Now there were all these technical derivations, but if you are lost in them, just remember this equation. Now what this equation tells me is that basically, given any magnetized system, you have your material, you put it in a magnetic field, it will be magnetized. Once it is magnetized, you can describe the magnetization just as if there was some additional currents in my system. Some volume currents, which are given by the curl of the magnetization, and some surface current, which is given by this cross product. It's just like if you remember our electrostatics, when we have our material, we put it in an electric field, an external electric field, or an electric field created by the charges we put, the medium became polarized, and this polarization we could describe as some bound charge density, as some surface charge density. Just like that, the magnetization, we can describe it in terms of some bound current density and bound surface currents. Now, what are these currents? And we started discussing them. Now, we said that if you put your material in some magnetic field, it will be magnetized. So either the magnetic dipoles will be aligned, or there will be the magnetic dipole moments of the atoms will change in the opposite direction of the magnetic field. So let's say it will be magnetized in this direction. Let's say the magnetization is kind of uniform and it is given by this direction. So if we just imagine, for example, one of the electrons orbiting an atom, which direction does the electron orbit? If the magnetization is towards you? Counterclockwise or clockwise?
Counterclockwise.
Who says counterclockwise? The right-hand rule, right? Right. So this is the magnetization, wrong. Electron is negatively charged. So electron is orbiting clockwise. So this is the motion of the electron. The current is running counterclockwise. Well, the neighboring atom, etc. So all these atoms, typically the currents will be running in the counterclockwise sense. You see, if there is an observer, if you can somehow manage to look at this point, you will basically see a current running in this direction. There will be a current at the edge. Well, it's not typically a typical current in the sense that if you follow these charges, they will not be going around the surface, but at any given point you have moving charges. So at that point there is a current running through our system. And the current is in the counterclockwise sense. Or you see, this is our normal direction, this is n hat. I is in the direction of m hat cross n hat. And its magnitude is also the magnitude of m cross n hat. If you look at this point, inside, well, there is a current running counterclock in this sense, due to this loop over here. There is also another current running in this direction due to this loop. So the sum, well, there's no current running at that point. If, of course, assuming these two currents are the same, in that case, the magnetization at this point and at this point will be equal. If the magnetization is equal, that's constant, there won't be any current. Well, if the magnetization is not constant, so then one of these currents will be larger than the other one, depending on which has a larger magnetization. So there will be some residual current left after the cancellation. The cancellation will not be complete. So if the magnetization is not uniform, then we also have such currents inside our material. And that is basically this volume current density, the curl of M. Now let's do some examples. Well, let's look at a sphere, which is magnetized uniformly. Now, to calculate the magnetic field that this uniformly magnetized sphere creates, let's look at the currents, the corresponding currents. We have the bound volume current density, which is the curl of M. What is the curl of M? M is uniform. Zero. M is constant. So this is 0. So outside there is no current. Inside there are no effective currents. There are cancellation between the effective currents of neighboring dipoles. They just cancel exactly. Now then we can talk about the surface current. This is M cross N hat. Well, to be able to calculate it in a better explicitly, write it explicitly, let's just choose some coordinate axis. This is Z, X, Y. This is my origin at the center of my sphere, so that N hat is nothing but R hat. So this is equal to M in the Z direction cross R hat, M Z hat cross R hat. So what is the magnitude of this bound charge density, surface current? What is the magnitude of Z cross R hat? Sine theta. What is the direction of Z hat cross R hat? Well, let's see. This is my sphere. At this point, okay, z hat is upward. This is my r hat. Z hat cross r hat is into the screen at that point. At this point over here, this is a sphere. So we can look at this point over here, out of the screen. So this is my r hat. This is my z hat. Z hat cross r hat is now in this direction. So it is rotating around this sphere. Well, that is our phi hat direction. So KB is actually m times sine theta in the phi hat direction. Well, basically we had solved this problem already. We had this sphere which has a uniform surface charge density, and it was rotating with angular velocity omega. And now we said that the surface charge density is just sigma omega cross r, which is nothing but sigma omega r sine theta. Well, r is the radius of the sphere. So just look at if you just pick up our previous solution, and instead of sigma omega r, you just put the magnetization up, and we know the answer. Now, if you remember this problem we had solved by using the potential. Magnetic scalar potential, not the vector potential, but the scalar potential. We had, because inside the sphere and outside the sphere there were no currents, so the curl of the B field is zero both inside and outside, and hence we could define a scalar potential inside and outside. And then this potential satisfied the Laplace's equation inside and outside, and then we determined the coefficients by just matching the B field at the surface. And you can just pick up the result. Well, there was the B field inside, if I'm not wrong, it was 2/3 mu0 m. Well, the important thing is that it was uniform. There's a uniform magnetic field inside, and outside it is just curl of m cross r over r cubed with this mu0 over 4 pi, where m is the total magnetic dipole moment. We know the magnetization. Remember, magnetization is the magnetic dipole moment per unit volume. So if you take magnetization, it's uniform, multiply it by the volume, you get the magnetic dipole moment of our sphere. Well, let's look at another problem. Uniformly magnetized cylinder. Again, there is a uniform magnetization in my cylinder. Let's say it's pointing upward. So let's calculate the corresponding currents. What is the volume current density? Remember, it is always the curl of the magnetization. Magnetization is constant, uniform, so this is 0. The surface current density. It is m cross n hat. Well, in cylindrical coordinates, m is in the z direction. Let's choose this as our z direction, x, y, and z coordinates. The center is at the z-axis is on the axis of the cylinder. So the normal direction is nothing but s hat direction, the radially outward direction. So what is s hat cross z hat?
Yüzeye paralel.
Phi hat or theta hat or phi hat, whatever you want, or minus that one. Minus phi hat or plus phi hat. Plus. Let's see. This is z hat. Let's look at this point out of the screen. Z hat cross s hat. Z hat cross s hat in this direction. So towards your right. At this point. At this point, well, this is still z hat. This is my s hat. It's into the screen. So it is just rotating like this. That is the z hat direction. Just your thumb in the direction of z, your fingers will be in the direction of phi hat. So Km is just m times phi hat. There is a uniform current running on my system. Well, this is basically a solenoid and nothing else. Remember what a solenoid is. We had, in the case of the solenoid, we just described it as just there are wires running around. But those wires, the only purpose of the wires is to be able to create some uniform surface current density in the solenoid. Now, in this system, in this uniformly magnetized system, this is effectively a system in which has a uniform circular current running through my system. So just like the solenoid, we will have some B field inside, no B field outside. The B field inside will be vertical and uniform, etc. Any questions?
Yani hocam bu aslında dönüyor mu?
No, the cylinder is not rotating. I mean, you see, this is just a cylindrical magnet with a magnetization. We are assuming that it has a uniform magnetization. But this system is basically the same system as a system in which there is a surface current circling my cylinder. This system is identical to that one. And this is identical to the system in which we have a cylinder. It has a surface charge density, and it has an angular momentum omega. These systems are identical systems in the sense that they will be creating the same magnetic field. So in this system, the Kb would be just sigma omega r. So sigma omega r in one of them would correspond to the magnetization in the other one. So if you know the solution of one of them, you know the solution of the other one.
What is the relation between magnetic field and Kb? The formula that we also used in the previous example.
is the vector potential, there will be a contribution from any current, from the surface current, from the volume current, if there are anything. Or let's say, let's just review this one. You see, we have this system with uniform magnetization. We said that this is equivalent to a system in which there is a surface current. KB. And KB was nothing but M in this example. So we can use the Ampere's law to calculate the B field. Now outside B will be 0. Inside B will not be 0. And B will be perpendicular in the Z direction. This is B. B will be, it might depend on the S. It can't depend on the phi coordinate. It cannot depend on the Z coordinate. And it will be in the Z direction. So we can just imagine such a hypothetical loop, A, B, C, and D. Let's say this length is L. B dot dl around this loop should be equal to mu0 times I enclosed. Now, the integral B dot dl, we can divide it into 4 parts around our loop. It will be B dot dl from A to B plus B dot dl from B to C plus B dot dl from C to D plus B dot dl from D to A. And then if you just look at each one of them, let's see, from B to C, the top segment, the B field is either perpendicular to dl or it is 0. In both cases, B dot dl is 0, so the second term is 0. From C to D, this is already 0, B is 0. From D to A, either B is 0 or B is perpendicular to dl, so B dot dl in any case is 0. So these 3 terms, they are 0. Now from A to B, dl is in the Z direction. From A to B, bs in the Z direction. Scalar product with dl in the Z direction. This is equal to bs times h. But we also know that I enclosed is here we have an area. The area is perpendicular to the current. Since the area is perpendicular to the current, or this line segment over here, the current only passes through this line segment. That line segment is perpendicular to the surface current density. So the total enclosed current is just KB times H. Positive or negative?
H is L, right?
H is L, yes, sorry. Now the enclosed current, is it positive or negative? It is positive. Just use your right hand again. Curl your fingers in the direction of the loop. Your thumb points in the direction of the current, of the positive current. If the current is running in the direction of your thumb, it is a positive current. If it is running in the opposite direction, then it's a negative current. So we know that Bs times L is equal to mu0. Kb is just M times L. L's cancel, so Bs is equal to mu0 times M. Well, there's only one thing left to prove. How do we know that the B field outside is 0? We claimed it to be 0.
Silindir sonsuza kadar gidiyorsa
So
dışarıda 0 olur.
why? That is what we claim to be true. But why?
Amper zorluğunu tekrar yaptığımız zaman bu sefer daha büyük bir tüm sistemi.
So
Yani bir ikileri uzattığımız zaman giren akım çıkan akım eşit olacağı için
you mean this length, this side? Okay.
uzatırsak diğer tarafa doğru
So this loop we can just move it to the other side. Okay. So
B'den diğerler sıfır gelecek.
okay.
Close
No, not the, B dot dl will not be 0. I mean, you are saying that let's move this segment inside the cylinder so that it goes outside. Okay, the integral of B dot dl is 0 because the net current will be 0. That will basically tell me that the contribution from this segment will be minus the contribution from this segment. But how will it tell me that those contributions are separately 0? You see, in this sense, in this side, the dl is going downward. On the other side, it is going upward.
Dışarıda magnetiz değişmiyor.
So, I mean, so you didn't ever play with a magnet, right? Outside a magnet, there is no magnetization. So your claim is that since there is no magnetization, no magnetic field. But you're almost on the right track. Now you're on the right track. Just take one more step. As your friend pointed out, we can imagine another Faraday loop, Ampere loop. Let me look at this one. I mean, it doesn't really matter whether the two vertical sides are on the same side of the cylinder or on the other side. It will not make any difference. Let's give them names, A, B, C, and D. Let's say this is our S0. This is our S1. So the distance of both of the vertical segments. This form of B we will still use because this depends on the symmetry of the problem. Under rotations, nothing changes, so nothing can depend on phi. Under translations in Z, nothing that changes, so nothing should depend on Z. So the magnitude can only depend on S. And due to the symmetries, well, there is not much alternative. The B field can be cylindrical, circular, but if you would assume the B field is circular, just take a circle inside and evaluate B dot dl. If B field lines are circular, B dot dl will not be 0, but there is no current passing through it. So they cannot be circular. In fact, the only alternative is that it should be in the Z direction, both inside the cylinder and outside the cylinder if there is any B field. Now we will just show that outside there cannot be any B field. So this is my system. Let us just evaluate B dot dl. This will be just a contribution from B to C, Bs in the Z hat direction, dot dl in the Z hat direction, plus from D to A, Bs in the Z hat direction, scalar product with minus dl in the Z hat direction. Let's call the height h. From the horizontal segments, since B field is in the Z direction, the horizontal segments dl is perpendicular to the Z direction if it is non-zero. So there's no contribution, so that's why I didn't write it. But you see, in the vertical directions, S coordinate is just a constant. I can take it out of the integral. So this will be equal to, from B to C, the S coordinate is S0. integral of from B to C of dl. From D to A, the S coordinate is S1. Minus integral of dl. Well, the dl integrals in both of them, it just gives us h. Times h. This should be equal to 0 because there is no current passing through my loop. And this basically tells me that Bs0 should be equal to Bs1. And this tells me that outside the magnetic field, if there is any, it should be constant. It should also, I mean, before, just due to the symmetry, we said that the magnitude cannot depend on phi, the magnitude cannot depend on z. But now we had shown that the magnitude outside the cylinder also cannot depend on s. It has to be the same. Well, if you go to infinity, it should be 0. So it should be 0 everywhere. Of course, assuming there is nothing else that creates a B field. Outside the cylinder, there is no B field. Now this kind of completes our proof.
S sıfıra gidince tamamen B'ye mi dönüşüyor?
Well, you see, we are looking at outside the sphere. Outside the sphere, S can never be 0. Inside the cylinder, we know that this is Bs. This means 0 times the magnetization.
Hocam bu manyetik alanın böyle bir noktadan çıkıp tekrar bu noktaya dönmesiymiş.
Well, it goes to infinity. And you can imagine that at infinity, it just goes back around and goes to the other infinity.
Does there any similarity with the electric field and displacement relationship?
We will see that in a moment. So let's look at the curl equation. So what became of that? We know that curl of B was equal to mu 0 over 4 pi J plus JB, the bound current density, if there is a magnetization in our system, which is mu 0 over 4 pi. No, sorry, not 4 pi, mu 0 J plus the curl of M. Curl of M is the bound charge. And Well, the bound charge is not really something we can control, so we would rather obtain an equation. Just like in the case of in electrostatics, we define the displacement field mainly to obtain an equation that doesn't involve the bound charges. Now, we would like to do the same thing over here. We would like to obtain an equation that doesn't involve the bound current density or the magnetization. It should only depend on the free charge current density. And to do that, you just move the term that contains the magnetization to the left-hand side. The curl of 1 over mu 0 times B minus M. This is equal to J. This is basically the equation we have. And instead of the displacement field, this is what's called the H. So curl of H is equal to J.
Bu H dediğimiz şey displacement.
It is analog to displacement. If you remember, the displacement field was the electric field plus the electric field created by the bound charge density. Similarly, this H is created by the B field and also the bound current density. Now, just a warning about the naming B field. Sometimes it's called the magnetic field. Sometimes it's called the magnetic induction field. Basically, because it creates, we will see that it is the field that is responsible to induce electric current somewhere else. This H field, well, if B field is called the magnetic field, then it's usually called just the H. It doesn't really have a special name. In some places where the B field is called the magnetic induction field, it's called the magnetic field. Just keep in mind that they have different names, and in different texts, their names are just intermingled with each other. Just to be on the safe side, H field and B field. Now, how do you create an electric field? Practical terms. How do you control the electric field that you create?
We have two plates, we apply a voltage, and then we charge those two plates, so there will be an electric field between these two plates.
So
By changing the voltage, we can.
Great. So basically, by creating a potential difference, you create an electric field. So that's what you can control. By modifying the voltage, you control the electric field that you are applying, or that's created, in fact. So how do you create a B field or an H field?
We have coil. No, not coil. What was the name of the inductor? No, not inductor.
Solenoid.
Yes, solenoid. And then we have a current turning around it, and by changing the current, we can set the.
Basically, you control the current, but the current that you control controls H. Okay, so what you are, in practical terms, what you are actually controlling, you are controlling the electric field and you are controlling the H field, not the B field. That will be important, this distinction will be important when we define some susceptibilities, etc. But that, well, let's give a break now, a 10-minute break, not 15 minutes. And then we will continue with this magnetostatics in material.
John, what is the difference between H field and B field?
This is the difference between the H field and the B field.
You said both of them are magnetic.
It's just like E field and D field. What's the difference between the electric field and the displacement field? They are different quantities. They are related quantities, but they're just different. In a sense, the H field is like the magnetic field without the magnetic field due to the magnetic polarization. Magnetization. In a sense.
İkiniz de gitseniz.